This last unit talks about the ways that we can apply the laws of thermodynamics to understanding chemical reactions in different ways. So, thermodynamics is all about the flow of energy and how it can cause physical and chemical changes to happen or not happen. There are several laws of thermodynamics, starting with the Zeroth Law. And the nice thing is, we don't have to know them by name. We just want to be able to apply them to understand which things are likely to occur chemically and physically, and which things are less likely to occur chemically and physically. So we talk about that in terms of thermodynamically favorable things or thermodynamically unfavorable. And this is going to extend our definitions when we've looked at enthalpy. Enthalpy is all about heat and temperature, but there's also other ways that energy can be involved and thermodynamics can be involved in terms of making a reaction occur or not. The first key to that is an understanding of the term entropy. Entropy is formally defined as the dispersal of energy, but a lot of times we kind of simplify it as in our system, we're thinking about the randomness or the disorder. So entropy itself is disorder. We can define it lots, even more kind of formally or more precisely by talking about all the microstates or all the different ways I can arrange my molecules within a system that is still the same system. All of those are different ways of just saying, when I look at what I'm starting with compared to what I'm ending with, how neatly arranged or orderly is that? The natural flow of entropy or disorder in the universe, according to laws of thermodynamics, is that entropy in the universe will always increase, meaning that if we don't have any intervention, the system is going to disperse energy or it's going to become more and more disorderly over time. The classic chemistry teacher example of this is thinking about your bedroom. If you don't do the work to clean it up, it's just going to accumulate more and more dirty clothes, more trash, more dishes, and it's going to get more and more disorderly over time. And that's going to be the natural flow unless there's something to stop that. For the universe as a whole, it only flows that direction. But we can look at individual systems to see, are those systems themselves becoming more orderly or disorderly? In terms of entropy, we can compare states of matter, and that's usually the most important way to describe entropy. Solids are the most orderly, most neatly organized, most compact, and least random. Liquids are still compact, but moving more freely, so more randomness and disorder. Solutions, especially solutions of maybe an aqueous solution, are a little bit more disorderly. We have a liquid mixed with some sort of solute, and they're intermixed together. There are a few exceptions to that, but in general, we would say solutions are more, but the most disorderly is gases. So we have this picture here that kind of shows it both with color, with arrangement, but where we're going from a nice, neatly arranged, maybe crystal or solid formation to a much more spread out, much more random, much less attracted arrangement of that. Another way we can change the entropy is that when I have a big molecule or just something that contains lots of atoms all connected together, and that breaks apart into its smaller pieces, like a decomposition reaction, those smaller pieces now have more ways that they can spread out and move around more randomly. When I change the size of my container, specifically for a gas, because solids, the size of the container doesn't matter, same with solutions and liquids. But when I do it for a gas, now the particles can spread out more and can arrange themselves more different ways. The hotter my system is, the more I increase the temperature, the faster those particles are moving, and therefore even more random in their motion. And then kind of like up here, in general, mixing two things together is much more random than having the two pure substances. So a lot of times we're looking at this qualitatively. We're comparing reactants to products or starting to ending to see how does the randomness or order of the system change. When we're doing this, and we'll do examples, it's really important to use words like orderliness, randomness, dispersal of energy, not just saying, well, it goes from solid to gas. Why does that change the entropy? But we can also look at it from a quantitative sense. Much like delta H that we've done before, we have an equation. The change in entropy for the system is the sum of the absolute entropies for my products minus the sum of the absolute entropies for my reactants. As individual values, those absolute entropies aren't super helpful, but they do allow us to calculate that change. Some important things that we'll see as we do this in the equation is the unit is joules per mole Kelvin, because different temperatures change our entropy. And obviously, it would be an amount per mole, not per individual atom. And then it does relate to the amount or the dispersal of energy. So we want to be able to use this conceptually, but also apply it mathematically.